Hello, everyone. My name is Zongyao Liu, a PhD student from the University of Texas at Arlington. In this presentation, I will introduce our work on uncertainty estimation framework for probabilistic object detection. My co-authors are Nolan Gutierrez and our supervisor, Professor William Bexey. In this work, we propose a framework that employs two uncertainty estimation techniques in object detection task. Object detection is the task to find out what are the objects in an image and where are the objects. Object detection is an important part of the perception system of robots and autonomous systems. Although significant development have been made in object detection in the past decades, in the real world, we see common problems, including those due to occlusions, as shown in the image on the left. This image shows two common issues that may occur in standard object detection. The bounding box that localizes the dog does not cover the entire body of the dog because the tail part is occluded by the cat. Furthermore, the object detector is confident in its incorrect prediction, which mislabels the cat as a dog. Such issues make deployment of object detection systems unreliable in the real world. To alleviate these problems, probabilistic object detection has been proposed. Probabilistic object detection extends upon conventional object detection by requiring an expression of spatial and semantic uncertainty. As shown in the image on the right side, the bounding boxes now become probabilistic bounding boxes with spatial uncertainty expressed as a covariance matrix on each corner. Additionally, semantic uncertainty is expressed by providing a probability distribution over the known classes for each detection. Since the objective of the detection is different, the original evaluation measure for standard object detection, namely mean average precision, is not sufficient to evaluate the performance of probabilistic object detection because mean average precision does not reward the estimation of uncertainty for the predictions. Therefore, we seek to use the probability-based detection quality to measure the performance of probabilistic object detection. As opposed to average precision-based measures, PDQ jointly evaluates the quality of spatial and semantic uncertainty, as well as traditional detection accuracy. We refer readers to the original papers for detailed introduction of PDQ metric. There are different ways to quantify uncertainty in deep neural networks. Bayesian neural networks are the most natural way to provide a mathematically grounded foundation to reason about uncertainty in deep neural networks. To reason about uncertainty, this method operates by learning a posterior distribution over the weights of a neural network. However, the prohibitive cost of computation hinders the practicality of Bayesian neural networks. Dropout was first proposed as a technique to prevent overfitting for deep neural network training. Whereas dropout is normally utilized as a regularization technique, dropout at test time from a Bayesian perspective can be explained as a way to deal with the model selection problem by Bayesian model averaging. From this standpoint, Monte Carlo dropout was proposed as a tractable approximate Bayesian inference for uncertainty estimation. Deep ensembles was proposed as a non-Bayesian method for uncertainty estimation, where an ensemble of multiple individual networks is obtained by training each network with randomly initialized parameters. And when combined together, each network is expected to behave differently for given inputs, hence expressing uncertainty. And in this work, we combine MC dropout and deep ensembles and apply them jointly with two pre-trained object detectors to obtain a unified framework for probabilistic object detection. The network architecture of our framework is shown in this figure. Our system can be applied to any pre-trained detection models. For a given image, we first apply test time augmentation techniques on images with very low brightness to make the detection easier. Then the image is sent to two detectors to perform the detection separately. The two base detectors that we used for ensemble are hybrid task cascade and grid RCN. Each pre-trained detection model is finely tuned for exceptional performance. And we refer readers to the original papers for their detailed network architectures. Here, for simplicity, here we only use the cube to indicate each detector. For each single detector, we retain dropout layers during test time for doing uncertainty estimation. First, we obtain a set of bounding boxes from both detectors, and then we combine the results and merge them together into one single result according to intersection over unit. The final prediction for each detector of every image defines a bounding box, a covariance matrix, a predicted class label, and a confidence score. This algorithm shows the detail of how to merge the ensembles of two detectors. To merge predictions, we group detections by intersection over unit using non-maximum suppression. And we keep the most confident detections from each observation. First, non-maximum suppression partitions boxes into groups such that any two boxes in a group has an IOU above a threshold lambda between 0 and 1. Each group is sorted by confidence scores. The list of boxes contains the top left and bottom right corners, and the confidence of each box's label. Next, each of these observations represented as groups of bounding boxes are reduced to most confident bounding box and label. Finally, the covariance matrices of every detection are computed to express the uncertainty of the predicted bounding boxes. Besides the major two uncertainty estimation techniques we used, there are also certain metrics we found that can affect the PDQ score. I will dive into some of the implementation details for each heuristic that we apply to produce our results. First, we apply threshold filtering to reduce the number of false positives by removing detections with confidence scores below an empirically obtained threshold. Second, we apply bounding box reduction to reduce the number of background pixels labeled incorrectly. We can reduce the height and width and maintain centers for each bounding box by a certain proportion. Third, we improve false positive label quality by keeping the value of the highest score for each bounding box and setting all other scores to 1 minus highest score divided by 30. 30 is the number of classes of the dataset. Fourth, we calculate the covariance matrices associated with the top left and bottom right corners of the predicted bounding boxes. To increase spatial quality, we set the X variance to arbitrary ratio times box width and the Y variance to arbitrary ratio times box height. These values will fill the diagonals of the covariance matrix for the top left and bottom right corner of each bounding box. And finally, we employ non-maximum suppression as an additional heuristic. We found that adding an additional NMS post-processing step can improve the score. And to avoid the situation that allows the evaluation of low confidence bounding boxes to increase the number of false positives, we allow larger confident boxes to absorb smaller, lower confident boxes to reduce false positives. Our experiments are conducted on a publicly available dataset that is provided by a previous probabilistic object detection challenge. This dataset consists of video sequences captured from simulations. Here are some images that we take from the dataset. And the base detectors we used for ensembles, as mentioned earlier, are hybrid test cascade and grid RCN, which are both pre-trained on COCO dataset. And the following are the results from various experiments with both ensembles and single object detectors. So the first table here shows the results of the ensemble model with different confidence threshold on the dataset. In our experiments, better performance can be achieved with lower threshold. The second table shows the effect of reducing the bounding box size of all detections on the PDQ scores. Here we found that reduction of the bounding box size by 10% results in better performance. The third table shows how the PDQ score changes when scaling the covariance to a different percentage of the box size. We experimented with covariance matrices dependent on the width and height of the bounding boxes. After exploring various values in our implementation, we found that setting the top left and bottom right elements of the covariances matrix equal to a scale of 30% of bounding box size give the best results. And we compared our merging strategy, which takes the most confident box with taking the average for ensembles. As shown in the table, our strategy significantly outperform averaging. Our hypothesis is that we should allow the detection system that is most confident in its result have its prediction take over the observation. And the last table shows the results of the individual HTC and grid RCN detectors, as well as their ensembles. We examined MC dropout as the uncertainty estimation technique on the HTC and grid RCN detectors individually, and also on their ensembles. In practice, this method is equivalent to performing several stochastic forward passes through the network and then taking an average of the results. We choose to sample 3 passes by adding a dropout rate of 0.3 to the second fully connected layer of HTC's region of interest head. After testing a large number of parameters, we found that the models that using dropout consistently demonstrated better quality when compared to models without dropout. And such result of an ensemble model with dropout outperforming an ensemble without dropout demonstrates the effectiveness of our idea for integrating these 2 approaches. And as a summary, in this work, we present an uncertainty estimation framework for object detection tasks, which unifies 2 popular uncertainty estimation approaches and uses the recently introduced PDQ measure as the evaluation metric and achieves a competitive score on the probabilistic object detection challenge validation dataset. And this is my presentation. Thank you.